We're going to start in analyzing the motion of objects by thinking about only motions along a line. And we're going to do a lot of, I'm going to bring up a lot of different quantities that relate to motion of objects along a line before I talk at all about motion in 2 dimensions or 3 dimensions. What we're going to see when we do eventually get to 2 dimensions is that we can use these same exact tools that we're using along a line to describe stuff in 2 dimensions with just a couple of sort of new kind of extensions of ideas we've used. Okay, so we are going to start completely with motion along a line. And I'm going to introduce, the idea of a measured time. I'm going to introduce the idea of position. These are the 2 things that I'm going to talk about in this little lecture segment. But then after that, I'm going to talk about velocity. And all of these things, you use these words in everyday speech, but in everyday speech, we don't have a real clear mathematical definition of what these are. We're going to have a very clear mathematical definition of what each of these things is as we talk about it. Velocity, and then as you might imagine, acceleration, because I've already talked about the derivative relationships between position, velocity, and acceleration. And then once we've gotten through those, we'll go on to talking about an object's mass. And then we'll talk about forces. And we're going to put all these things together with derivative relationships and other equations. And we're going to do all this just along a line before we move on. Okay, so we're going to start by talking about a relationship, relationship between time and position. And I'm going to start by saying what I mean when I talk about a measured time. You can think about this entirely in terms of a stopwatch. I think that's a good way to do it. So, for a stopwatch, I'm thinking of, this could be like a handheld thing that has minutes and seconds on it. And you might have a button up here to start and a button over here to reset, And so we're going to say that always our time t equals 0 is going to be when we turn the stopwatch on. And at the point that you turn it on, these numbers will start scrolling. And we always are going to turn the stopwatch on when some relevant thing happens. So when the start of some kind of motion happens that we're describing, when we're given information about the motion of an object, that's when we're going to say, okay, this is when we start it. That's time equals 0, and everything else is going to be measured after that. So other things happen at, positive times. We're never going to go backwards in time from when we turn a stopwatch on. And this key instant, time equals 0, is always going to be so this is always going to occur at some relevant instant when we're either given information about the motion. You know, we might know the speed and the direction the object's moving at that instant, or we might know that the object's at rest, or it might say that this is the start of the motion. But it's always going to occur at some relevant instant when either stuff is known about the motion, or stuff is asked for. Okay, so it's always going to be at an instant when we either know stuff or we want to know stuff. As the stopwatch goes forward, as time goes forward, we're going to always be noticing, we're always going to notice the location of the object at each given instant. T. Okay, so that's all you have to know about our measurement of time. You can think of it as a stopwatch. You're going to turn it on when something important happens, and then you're going to track the motion of the object as the time scrolls on the stopwatch. We're in this class just always going to use SI units. I'm not going to make you do a lot of conversions, but you do have to know the SI units for everything we talk about. And so the SI units for time are seconds, and we're just going to abbreviate that as a lowercase s. Now the position, a lot of times I think in everyday speech, we think of position as the same thing as location. Well, a location doesn't necessarily have numbers associated with it. You know, Yosemite Park is a location, but we don't have a number associated with it. You get a position when you set up a system of measurement that allows you to put a position onto an object's location. So what we are going to do to measure the position of objects, and this is all imaginary, you don't necessarily physically do this, but first we are going to imagine a number line along the line that the object is moving. Remember, we're only talking about motion along a line. And you can think of a number line as like a ruler, but on a ruler, they don't ever show negative numbers. I mean, you could think that the negative numbers start at the zero of the ruler and go in the direction that, you know, off the end of the ruler. But we're always going to imagine this number line having a positive direction and a negative direction. And we are going to always place the zero of the number line at the location of the object when the stopwatch is turned on. Okay, you can think of that as we're always going to put the zero of the number line at the object's location when time is equal to 0. So that's when the stopwatch is turned on, and you can think of that as time equals 0. Now that we have a number line in place along the line that the object's moving, at a given t, so that's when the stopwatch says t could be 5 seconds or 20 seconds or half a second, but when that time comes up on the stopwatch, that's our given time t, and the position of the object is its location along the number line when the stopwatch says t. Just like a ruler has units on it, you can get rulers that are in inches or millimeters or whatever. We're going to always measure position using units, and we're going to use the SI units. And the SI units for position are meters. And we'll represent that with a lowercase m. Okay, well, let's think about an example. And for this example, I'm going to imagine that, it's a pretty simple setup. We just have so here's someone's hand. Something's wrong with their hand, but anyways. And they drop this ball, and they drop it from a height of 2 meters. Obviously, this isn't drawn to scale very well, but they drop it from here. And we know that the height that it's dropped from is 2 meters. Okay. And let's say that somebody observing this uses a stopwatch to measure this motion. Okay, well, let's first think about the stopwatch. So at this instant, when the object is dropped, here's our stopwatch. And this is the instant when, boom, the action happens. The person presses the button. Right here, the stopwatch is moving, but it says all zeros. Okay? And then say that we're told that it takes 0.64 seconds for this object to hit the ground. Okay, so when the object hits the ground, this stopwatch says 0.64 seconds. We don't have to press this button. We just have to observe what the time is when it hits the ground. And so that tells us the times here. What about the positions? Well, we have to choose a number line. And I said that we're always going to choose our number line to have 0 happen when the time is equal to 0. So we're going to put our 0 right here when the ball is dropped and the watch is clicked. So here's our number line. And now we have to choose one more thing. We have to choose whether our positive, this object is going up and down. It's going vertical. So we're not going to put our number line, we're not going to put it horizontally. That doesn't measure the motion. So we only have 2 choices for what we're going to call positive and what we're going to call negative. We can make positive up and negative down, or we can make positive down and negative up. And you could make either of those 2 choices. When I'm doing vertical motions, I tend to always make my positive up. There's no reason you have to do that, but I tend to. And so I'm, in this example, going to call positive this way and negative this way. Okay, and now what I want to do is think about what the position and time are at the two instants that we've had described. We have the instant where the ball is dropped, okay? We know that the time is 0 at that instant, and we also know that the position is 0 at that instant. You'll see that if you always put your 0 for the number line where the object is at time 0, then your first position is always going to be 0. That's just kind of like a definitional thing. That's just how it has to work. And then, okay, so the position is 0 at time 0. And then the second instant, the time is 0.64 seconds. And we have to think about what the position is of the ball at 0.64 seconds. Well, the ball has traveled 2 meters. It started at 0, traveled 2 meters. If you start at 0 and go 2 meters in the negative direction, your position just has to be negative 2 meters. You could imagine that if we put all the, hash marks on this number line, this would be negative 1 meter. This is negative 2 meters. Positive 1 meter would be up above the hand. And so we have our two instants. Our instant 1 is when time is equal to 0 and the position is equal to 0. And our instant 2, when it hits the ground, the time, the stopwatch is going to say 0.64 seconds. And the position is going to say negative 2 meters. And a very common way to represent this, you can think of position as being a function of time, and we can draw a graph of position versus time. We're always going to put time on the horizontal axis and position on the vertical axis. And our relevant times are going to be, well, let's say this is 0.5 seconds, this is 0.6 seconds. And so our relevant time is going to be a little more than that. Our position, we'll say that's positive 1 meter. That's negative 1 meter. That's negative 2 meters. And so our first instant is going to be this point on the graph. And our second instant is going to be at time 0.64, time position negative 2, and so something like that. And we can connect these. It turns out if you drop something, it's not going to be a straight line like that. We'll talk about that later. But for now, this is a perfectly good graph, position versus time graph of that motion. I want to do another example, and this time as we go, I recommend that you pause the video when I say to and try to come up with the answers that I'm looking for. That way, when I say it, you can see whether you're understanding it or whether you're a little confused on something. So here is another example. Let's say that we have a ball that rolls up a ramp. And it rolls up the ramp a distance of 0.5 meters. Before, since it's rolling up the ramp, gravity will sort of slow it down. Eventually it'll reach a highest point, and then it'll turn around and roll back down the ramp. So it rolls up the ramp 0.5 meter before turning around. And rolling back down. And so if we are told that it takes 0.6 seconds to reach its highest point. And an additional 0.6 seconds to return to its starting point. Draw position versus time graph of this motion. The one extra bit of information that you need if all of our graphs are going to look the same is you have to know which way the number line is going to face. I'm going to remember the number line is always in line with the motion, so it's going to be parallel to the ramp. Let's choose the positive direction to be up the ramp. So we're going to choose the positive direction. Up the ramp. Okay, well, following the steps that I did in the last example problem, see if you can figure out the time and the position at each of the two instants that are described, and then plot those on a position versus time graph. So pause the video now and see if you can do that. Well, I'm going to start out by sketching what's going on. So say this is the ramp. And the ball starts out here, and it rolls up the ramp this way until it gets to this location. That's the highest point, and we're told that these two are 0.5 meters apart. And then the ball's going to roll back down. I'm going to, so for the stopwatches, at this instant, we're always going to start the stopwatch at the earliest moment where we're given information or, looking for information. So that's going to be the start of the motion here. So I'm going to say at instant 1, the stopwatch says 0.0. And then we get up here, and if you look at the stopwatch, got to draw it a little bigger. Yikes. Okay, so if you, I guess I'll draw the stopwatch down here, but the stopwatch would say 0.6 seconds when it gets to the top. Then it's going to roll back down, and we're going to read the stopwatch a third time. And what's it going to say? Well, if it takes 0.6 seconds to get to the top, and then another 0.6 seconds to get here, the stopwatch is going to keep running. So this is going to say 1.2 seconds. Okay. And the last thing we have to do is put the number line down. It's going to be along the direction the thing is moving. We're always going to pick this point to be our 0. You don't actually have to do that, but I think it's easier. And now we have to choose a positive direction. And I said we're going to choose the positive direction to be up the ramp. So my positive is this way, and my negative is this way. And if you start at the point 0 on a number line and go 0.5 in the positive direction from there, when you get here, you get to a value of positive 0.5 meters. And so now we can write out what we know about these two, I guess in this case it's 3 instants. So instant 1 is when the motion starts. Time is equal to 0. And the position is equal to 0. Then we get up to the highest point. Time is equal to 0.6 seconds. Position is equal to positive 0.5 meters. We'll never have negative times, but we could have negative positions. That's just saying where on the number line the object is. And then the third instant, time is equal to 1.2, and the position is equal to, okay, so what is the position of the object? Well, with the times, we had to add it up. That stopwatch just keeps running. But it's not the same with position. With the position, you're just looking for where on the number line the object is. So when it gets up to this highest point and then rolls back down, it's back at this point that we've already labeled with a 0. And so that position is going to be 0. And now we can, now that we have all of these points, we can think about drawing the position versus time graph. This is the time axis. This is the position axis. The times that we care about, this is going to be 0.6 seconds. And then we're also going to have a 1.2 seconds. And the positions we care about are 0 and 0.5 meters. And now we can plot the 3 points, 0, 0, 0.6, 0.5, and 1.2, 0. Like I said in the last example, we'll find out later that this would have a curve to it, but for now, we can just connect it and think of the position versus time graph as being something like this for the motion.